Hello everyone, my name is Garrett Martin and today I will be presenting the Computer Vision Forest Inventory Analysis Research Team's poster on computer vision and machine learning for forest inventory. Jumping over to the introduction, it reads, Forest inventory analysis relies on manual data collection to assess the conditions and trends of forest development. Its applications are significant, but its process is labor and time intensive. Recent advances in remote sensing and computer vision have made it possible to automate data collection with consumer-grade cameras and analyze techniques that leverage machine learning. Here you can see a diagram of popular measurements we would like to extract from our trees. You can see here trunk taper, diameter taken at a breast height, and the first branch height measured from the ground. Down here in the platform section, we talk about what we use to capture our data. An Intel RealSense D435i camera is used to record footage and extract each tree's diameter at breast height, first branch height, and taper. Now, let's jump back up to the top to our methods and techniques section. Stand maps are used in forestry to visualize plots of trees. We can create these valuable maps with our code in 3 simple steps. First, generate a 3D point cloud with SLAM. Second, match point cloud data to GPS coordinates. And third, visualize trees as icons represented as green arrows in Figure 3, and overlay DBH measurements. Let's jump down to Figure 3 and take a look at it. Here is Figure 3. You can see here the rows of trees in our plot 115, which is where we record our data. Each tree is marked with one of those green upward-facing arrows. Now, let's go back up to methods and techniques. So for our second topic, we're going to talk about our segmentation neural network. Segmentation of depth images into trunk, branch, or ground classifications, as seen in Figure 2, will allow our team to gather more data, such as first branch height or taper of a tree's trunk. These are valuable measurements in determining a tree's lumber yield. Our segmentation neural networks architecture is based off of SegNet. So here you can see an image that we put into our neural network and what its output is. You can see that the branches are labeled in blue, the trunk in green, the ground in red, and the background in black. Now, let's jump to our conclusion section. Conclusion. Final product and goal. In the future, we will have a robust system composed of 3 interconnected components. The first component, the ROI, will be able to identify the tree's trunk, base, and first branch, output a data structure containing all the valid pixels of an individual tree. The second component, the attributes computation, should be able to extract attributes and perform computation with the valid pixels stored in the data structure. The third component, stand map generation, will be triggered when the first component detects a tree. Once activated, a point cloud of the tree will be built and added to the stand map with measurements annotated. Now, our main breakthroughs. Recently, our algorithm takes input in the form of a .bag file and exports a map with a point for each detected tree in a plot. In order to aid in tree trunk detection and analysis, we have developed the segmentation neural network to identify parts of a tree within RBG images captured by a stereo camera, which is what you saw over here in Figure 2 previously. Finally, to close our presentation, we'd like to present the overall view of our team with our main goals flowing all the way to our specific goals. You can see here that the dotted arrow represents things we're currently developed, and the solid lines represent things that we've already developed. And this concludes our presentation titled Computer Vision and Machine Learning for Forest Inventory for the 2021 Spring Undergraduate Research Expo.